Thanks, David, for the introduction, and I feel very glad to have the opportunity to teach this course because typically what we teach is a biostatistics course for graduate students, so it's actually also a new experience for me to teach to this audience. Before I got started, I want to ask the question, how many of you have had courses before, like basic biostatistics or basic statistic or probability? Quite a few. Okay, thank you. So this slide is from the previous lecture I think Stuart gave, and this one is on data types and representations in molecular biology. Actually, I have to warn you that for today's lecture, it will be very different from feeling like I'm fighting with a siren. So today's lecture, it will be very different from your previous lectures because today's lecture is for this series, it will be your first lecture on statistics, and especially for today, we will actually not going to get access to real data or real problem. It's really about, for today, it's really about probability. And so you will think a lot, but not really a lot of hands-on experience. But this is very important because most of my lectures later, and I believe for bioinformatics lectures as well, you always more or less are using probability, whether implicitly or explicitly. So today's task is really to understand what is probability and understand several important rules about probability. So, I believe you have learned descriptive statistics. So, what defines a descriptive statistic is really when you simply describe your data as is. You don't make inference. So, what do we mean by inference, or what do we mean by descriptive? So, remember this plot here, which you have a hypothetical population. And this population is if you have the ability to go to infinity number of samples, and that represents the total population that you're interested. And then keep in mind that whenever you want to understand or do some statistic or learn something about this population, the start point of you is always to get a sample from this population. So basically, your sample is a subset of your population. And then when you get a sample, and then when you're trying to use the sample to understand the population, you're really trying to estimate something from the sample and then doing inference about the population. So this is the whole fundamental concept of statistics, that you always infer the population from a random sample. So here, for example, if we want to put it a little bit more concrete, if I want to understand the mean of a population, let's say the mean age of the American females. So that's my population, American female, and I want to understand the mean age of that population. If I want to understand that, where should I get started? You need to get random sample. You get random sample of 100 women. You get another so some of you get 100 random sampled women, American women, and a different one of you doing the same experiment, and you get a different random sample. So basically, you can get as many as you want random samples. And from those samples, the key is the sample is representative of the population that you are interested. And the next natural step is you can get a sample mean. You can estimate a mean from your sample, a mean age, or mean weight, or mean BMI. So use those mean. You can draw inference and trying to understand the mean of the population. So here there is this rationale behind this is from the total population, different people draw random sample, and then different people have estimate of the mean of their corresponding sample. there's some randomness here, because if you draw this 100 women, the mean of those 100 women will be different from if you draw a different 100 women. So there's this randomness, or there's this uncertainty. So how do you describe this uncertainty or this randomness? And that is the problem called probability. So again, so this slide is really summarize what I have said. To make inference about the population mean or something else, we need to assess the degree of accuracy to which the sample mean represents the population mean. Because you have sample mean, and you want to use that to understand the population mean. So you need to assess the degree of accuracy. So our goal is really from sample to population, and that is called statistics. And to start with, your tool, what is your tool, is really probability. And the probability, if you understand that, is from this population, the probability decide the accuracy of your sample. So, randomness. Things may happen randomly. For example, if you estimate the mean age, if you estimate the treatment effects in different clinical trials, you get this 100 women or you get this 100 patients, they will give you different estimate of the mean or different estimates of the random effect, of the treatment effects. So probability is really a language of uncertainty, and it quantifies randomness. So today we will basically introduce you several very important theories in probability. So first of all, whenever we talk about probability, to put that in mathematical language, you are talking about a probability of an event. And that is defined as the likelihood of the occurrence of this event. So basically, what is the likelihood that this event happens? That is called a probability of an event. And if you think about it, actually there is a very natural way to estimate this probability. So, for example, this is a table that summarizes for different time periods the total number of male births in the United States. And then it also gives you, the second column gives you the total number of births. So you have the total number of male births, so boys. And then this is the total number of total births, boys and girls. And those are the numbers, or those are your samples. And what is the probability of a male birth? So basically, I ask you, what is the probability of a newborn baby turn out to be boy? So without knowing any knowledge, if you just have this table, how do you estimate this probability? You can estimate this probability by this number over this number. The ratio between A to B, that would be the probability of a baby turned out to be boy. So if you estimate that, you get this number 0.51 in 1965, and then you get 0.512, a very similar number in a different time period. And then in the third time period, you also get a very similar number. So this probably seems to be a little bit overkill, right? It's very natural that you should estimate this way. But it essentially illustrates how do you estimate probability from your sample or from your data. So probability of event defines the likelihood of this event happens. So in mathematics, if you want to estimate that, it's the frequency of the occurrence of this event divided by the frequency of all possible occurrence of other events. So this is basically probability is a ratio. It's a frequency of male births over the frequency of all possible births. So that includes female and male, baby girls and baby boys. So if you think about it, by this ratio, you can understand that naturally probability is a number that bounded between 0 and 1. The lower limit of probability of any probability is 0, and the upper limit is 1. So random experiment means an experiment for which the outcome cannot be predicted with certainty. But all possible outcomes can be identified prior to its performance, and it may be repeated under the same conditions. So the probability of event is really the relative frequency of the set of outcomes over an infinitely large number of trials. Basically, probability of event is a relative frequency of this event happens, the frequency of that, and over if you do this a lot of times. So basically this sentence, it tells you the two fundamental rules to estimate the probability. First one, you need to get this ratio. You need to get the frequency of the event that you're interested over the frequency of all possible occurrence. And second of all, probability, you can only reliably estimate that if you have very, very, very large number of trials. Basically, if you only have 2 baby births and you want to estimate what is the probability of a boy, it's very likely that both of your 2 births turn out to be girls. And you cannot estimate that, if by that estimate, you would estimate that the probability of a boy is 0. That clearly is a wrong estimate. And that the reason for that is because your sample size of the number of occurrences that you have collected so far for this sample is too small. So basically, when you estimate probability, you would like to be the total number, the denominator, the frequency of all possible occurrences as large as possible. However, in real life, experiments cannot be conducted in infinite number of trials. So basically, you would like to enlarge this denominator as large as possible. But in real life, you have to have a limit. You have to have a reasonable control. It cannot be that you survey the whole births in the whole world. So you cannot have an infinite number of trials. Therefore, a probability of events estimated from empirical probabilities that obtained from a reasonably large samples. And here we have some notation. And those notation, you will see those very frequently in your real study, in your own studies. And here we basically call this sigma sign is the set of all possible outcomes of a random experiment. So that is really a space, and that defines your sample space, and denoted by this. So if you have, going back to that baby birth example, you could, for baby born, it's either have to be a boy or have to be a girl. So this whole sample space contains boys and girls, male and female. So that's really your total sample space. And in mathematics or in statistics, we typically use this letter to represent the event. So here I can use A or B. Conventionally, you use capitalized letter to represent the event. And then you use this to denote, often used to denote an event. So a null space, this sign, which really represents that a space with no elements. So this basically means that the space has nothing in that. So your total sample space has no elements. And then if A is in your total sample space, we use this symbol, A complement. It's a set of all elements which do not belong to A. So sometimes you can understand that by logical operation side, the complement of A is basically not A. So that means that your total sample space subtract the A, the event A. So in that example of baby births, if you think about A represent the event of a baby boy birth, then A complement really is the total sample space, boy and girl, subtract the boy, the event of a boy. So you got the A complement is really a girl birth. And then we have several notations to represent different definitions. So the first one is A union B. So this one represents the set of all elements which belongs to at least A or B. So if you think about in logic symbols, A union B is really A or B. So that would represent the whole space that's defined by A and also by B. And then the next one is A intersection B. So this is a set of all elements that belongs to each of the set A and B. And the next one represents A is a subset of B. So basically that means if A is a subset of B, each element of A is also element of B. So probably have to draw some Venn diagram for you to understand. And you will find that actually when you do exercise of probability, those Venn diagrams sometimes comes really handy. So what we have here, this one we call the total sample space. And then you have an event which is called A. And then you have another event which is called B. So this set, the elements that So we have a concrete example here, which is really, I would say, probably you can solve that in minutes. So let's see, if A is a set of numbers and it contains 3 numbers, 1, 2, 3, and B is also a set of numbers, it contains a different 3 numbers, 3, 4, and 5. So we think about it, we will just ask you different sets definition by what we introduced. A intersect B in this example, that would be the overlapping elements that both resides in A and also in B. So if you think about those two sets of numbers, 3 would be the only number or the element that belongs to A intersect B. And then further, if we define this total sample size is the positive numbers, the positive integers from 1 to infinity, all the positive integers. And then if we let A equals to the set of even numbers, so 2, 4, 6, 8, and to infinity. So A complement would then define the set of odd numbers, because from all the side of positive integers, if you remove all the even numbers, what you have remaining is a set of odd numbers. And another 2 examples are when A is a set of 1, 2, 3, and B is a set of 1, 2, 3, 4. That basically means that A is a subset of B. And then when going back to the first example, if A is 1, 2, 3, and B is 3, 4, 5, A union B would be 1, 2, 3, 4, and 5. Does that make sense? So from here, we will start introducing laws of probability. So there are a set of laws that for probability. And as you study statistics more and more, you basically are exploring, different laws. But all those are based on several fundamental laws or several fundamental rules of probability. And today you will basically cover all of those. So the first laws of probability is, like we said, for all the events, for all possible events, probability is always a number bounded between 0 and 1. So it could be 0, it could be 1, but it cannot be beyond 0 and 1. So it's a number that always bounded by those 2 thresholds. And when is the probability equals to 0? And that goes back to the concept of the empty set right there. So a probability of an empty set, that probability equals to 0. And then when does the probability goes to 1? And that goes to the concept of the total sample space. Because whenever you have specified a total sample space, implicitly that means probability of this total sample space is 1. So that means if the total sample space includes all the elements that possibly could happen, it basically means the probability that your event resides in the total sample space is 1, because it includes everything, every possibility, right? And then if A is a subset of B, then probability of A is less or equal to the probability of B. So this gives you a natural connection between the sample space and the probability. If A, the sample space, is a subset of a different sample space, B, then it means that the probability of A happens is always bounded by the probability of B happens. And the next one is probability of A complement plus probability of A always equals to 1. So probability of A complement equals 1 minus probability of A. So those two rules are also mathematically you can understand. If you want to prove that very mathematically, you can understand in this way. So if A is a subset of B, if the sample space A is a subset of sample space B, what does that mean? That means every element in A must be an element of B. So that means probability A is if an element in A happens, that must means that that element is also in B. So that means that element in B also happens. So basically that means the probability of A must be bounded or less or equal to probability of B. Right? So the next one, if you want to prove that mathematically, A complement and A, those two together constitute the whole sample space, because A complement is defined as every element that not in A. So if you plus A and A complement, you get the total sample space. And then the probability of the total sample space is always 1. So that means the probability of A complement plus the probability of A is 1. So the probability of A complement is 1 minus the probability of A. So the next one, which basically is a very important rule of probability, is it relates to how do you define mutually exclusive events. So what do we mean by mutually exclusive events? It means that if two spaces have no intersection, thus two basically means it's mutually exclusive. So for example, if we go to the Venn diagram and we have example like this is A and this is B, and A intersect B is an empty set. Essentially, you cannot find an element that both in A and in B. So those two do not have overlapping regions. So that means A and B are called mutually exclusive. And if you want to extend it, you get the concept of if you have a lot of event space and any of those space do not interact or do not overlap with each other. So you have all those from A1 to, let's say, AK. All those are mutually exclusive. That means for every I and J here, AI intersect AJ equals empty space. So this basically defines a sequence of mutually exclusive sets. And those I give you just two examples that those two are mutually exclusive. Is this the same thing as intended? Good question. It's not. And we will introduce that later. So this gives you an example of what is in real life, what is a mutually exclusive event. It's actually happen quite often. Let's see your blood type. Blood type can be A, B, AB, or O. So A, B, C, and O. I think this would be A, B, O, and AB. So those 4 blood types would be mutually exclusive. If you think about the baby births, then a baby boy and a baby girl would also be mutually exclusive, because nobody can be either, both a boy and a girl. So you could have to be just one out of those two possibilities, and that is called mutually exclusive. And that goes to your question that what is the relationship between mutually exclusive and independent? When we introduce that, we need to introduce the concept of what is independent events. This is probably one of the most important concepts in statistics, is that when we talk about two events are independent, that means that if I know the outcome of one event, that provides absolutely no information on the outcome of the other event. So you can see, sometimes we see that those two events are independent. Sometimes in layman's language, we see those two events are completely irrelevant. So in statistical language, what we call that? If A and B are called independent events, that means probability of A intersection of B is the product of A and B. And then if you understand what is independent, the next concept is what is dependent. And that is just the contrary of independent. So that means knowing the outcome of one event will increase the knowledge of the outcome of the other event. So A intersect B, probability of this intersect set, does not equal to probability of A multiplied by probability of B. So if this condition holds, we would say A and B are dependent. On the contrary, if the previous condition holds, if the intersection probability equals the product of the two probability of the two sets, then A and B are independent. So we have introduced the concept of mutually exclusive, and then we introduced the concept of independent event. Is there any relationship between those two? Before we go there, let me give you an example, and let's see intuitively do we understand those two concepts. So we have two examples here, and in each example there are two events, and I want you to tell me whether that defines these two events mutually exclusive or it defines the two events mutually independent. So the first example, A event is it rained on Tuesday, and B event is it didn't rain on Tuesday. So what is the relationship between those two events? Yes. And then the next example is A event is the same. It rained on Tuesday. And B event is my chair broke at work. And those two would be independent. So intuitively, basically, you understand that mutually exclusive means the two events, only one out of these two can happen. It cannot be A and B. Means A and B, this intersection has probability 0. So that means those two events are mutually exclusive. And then independent, it means that knowing whether this day is raining or not raining doesn't really help you at all to know whether your chair broke or not break. So knowing the event of A happens doesn't give you any advantage or disadvantage to infer the probability of B happens. So this is called independence, and then the previous example is called mutually exclusive. Good question. Yes. So in probability, if you know that the A and B are mutually exclusive, so that means when A happens, B cannot happen. So these two, if A and B are mutually exclusive, they must be dependent, because knowing probability of A, it tells you the whole information about B, right? So when the two events are mutually exclusive, they must be dependent. But when the two events are independent, that has nothing to do with whether or not, like they're mutually exclusive or not, because it basically are talking about different things. Okay? Okay, so after we understand the independent and dependent events, then we come to this another very important law of probability. And this is important because this defines the whole fundamental concept of statistics. So this is a law. When A1 to AK, if they are mutually independent, the probability of that intersect happen equals to probability of the product of their probability. So this one, although it might sound very hard to understand at the beginning, it's actually nothing fancy. It's just extension of the definition of independence. Because if you think about it, the definition of independent is if A and B are independent, the probability of their intersection is a product of their probability. So what if you have more than two events? What if you have a sequence of events and each of those is mutually independent of the other? So if that's the case, you just extend from this two event case to this multiple event case, that the probability of A1 intersect with A2 until intersect with AK equals the probability of A1 to AK. So if I just talk like this, you would think this is so easy, right? I mean, you would think like this is mathematically it makes sense and it's not that complicated. So why did I make such a big deal saying like this would be the whole concept of statistics? And let me talk this way. Suppose you have a data, you have a group of sample, and let's see, the sample is really, you are interested in the BMI of the whole American female population. And then you go outside and you get 100 women. And each of them, you ask them or you measure their BMI. So what do you get? In your data set, you get you have x1 to x100. Each represents a BMI measurement of one sample that you have. So you have BM1I 1 to BM1I 100. And then in statistics, we always talk about And then the next rule that I'm also going to introduce is the addition rule, or the addition law of probability. This one actually is easier to understand compared to the previous law. So this one basically, because it's called addition, so it helps you to solve, or it helps you to understand, to estimate the probability of addition. And when we talk about addition, that's really relates to the union. So it tells you, if you want to estimate the probability of A union B, that equals the probability of A plus the probability of B, subtract the probability of their intersection. And from that Venn diagram, it's probably the easiest way to understand this law. So, like I said, the union of A and B is really the space that, both in A and in B. So the probability that when it happens, it really means that the space of A, probability of A, plus the probability of B. But here, you actually double counted a space, and that space is the intersection. So after you do the addition, you need to subtract that intersection area, which you actually counted twice. Does that make sense? So this is called the addition law of probability. And then from here, it will be very natural for you to understand that what if A and B are mutually exclusive? So by definition, if A and B are mutually exclusive, that means A intersect B is 0. So that means this whole set is 0. And a probability of empty space is 0. So if A and B are mutually exclusive, probability of A union B is A probability of A plus probability of B, subtract this 0. And that basically means that if those two events are mutually exclusive, the probability that they happen, both, the union of those happen, is really just the summation of these two. Then the next part is, what if A and B are independent? So if A and B are independent, you can also apply this rule with one more step. So if A and B are independent, by definition, that means probability of A intersect B is the product of A and B, right? So if the two events are independent, the probability of their union is A probability of A plus B minus their product. So this whole three set of rules is called the addition law of probability. And actually, you only need to understand this very first formula, and then you can use that to derive the next two, which is a special case. So here is just if probability of A union B does not equal to the summation of these two respective probability, then A and B are not mutually exclusive. And then if the probability of A intersect B does not equal to the product, then A and B are not mutually independent. So here's an example that for you to exercise on independence and understand the definition. So we have two events. A event is the first doctor makes a positive diagnosis, And then the second event is Dr. 2 make a positive diagnosis. So let me tell you that the probability of A event, basically, it means that the first doctor makes a positive diagnosis among all the patients that he have seen is 10%. And then probability of B event means that the probability of the second doctor make a positive diagnosis among all the patients that he has seen is 17%. So let me also tell you that there is a subset of patients, or there are some patients that they went to Dr. A and also went to Dr. B. So they went to both doctors, and both doctors diagnosed 8% of all patients as positive. So that means probability of A intersect B is 8%. So given those three numbers, probability of A is 10%, probability of B is 17%, and then probability of A intersect B is 8%. Given those three numbers, can you assess whether the two doctors are making this diagnosis totally independent or not? Essentially, it means whether A and B are independent events or not. And the way to check this is by definition. So you were given that probability of A intersect B is 8%. So probability of A multiplied by probability of B by the two numbers that you were given is 10% multiplied by, I think there's a mistake here, by 17%. So this should be 0.17. And then this product equals 0.017. And then the next step is just to compare your calculation with the numbers that you were given. If they are equal, that means A and B are really making their diagnosis independently, that the overlap is purely by chance. If they're not independent, that means when the first doctor gave a positive event, positive diagnosis, it tells you that more likely than random chance, the second doctor will also give this patient a positive diagnosis. So by those two calculations, 0.08 and 0.017 do not equal. So that means probability that A and B, those two events, are not independent and they are dependent events. Questions? So we have went over this. When A and B are independent, their probability of their union is the probability of their summation subtract the product of their probability. But when A and B are dependent, how do we compute the probability of A intersect B? So when A and B are independent, we know that their probability of intersection just equals to the product of these two probabilities. What if they're not independent? What if they're dependent? Then when you were asked, if you're asked to compute the probability of A intersect B, how do you compute those? So this definition helps you to do that. This definition called conditional probability. So what is conditional probability? Conditional probability, you probably have seen that a lot. It denotes this way. Probability of A, this conditional on B. So by this symbol right here. So this means that probability of A given B. intuitively, how do you understand this? This means when, suppose you already know that B happens, under this context or under this is already happening, what is the probability of A happening? So this is an intuitive way to understand conditional probability. It's really probability of A, one event, conditional the other event that has happened. So probability of A conditional on B. How do we estimate this, or what is the definition of this? This basically equals that the probability of A intersect B over the probability of B. So mathematically, how do you understand that? It basically means that if you know B already happens, so that really means that if you know B already happens and you are interested in knowing what is the probability of A happens, so that really means your total sample space now is changed from the whole sample space to the sample space that's specified by B, right? And then when you take this ratio, remember to calculate probability you need this ratio. It's really the ratio between A and B both happen over the frequency of A and B both happen over the frequency of B happen. So in that Venn diagram, you can actually understand that in a graphical way that a little bit easier. So if I ask you to do probability of probability of A conditional on B, that asks you the probability of A happens when B already happens. So from this Venn diagram, this space represents the sample space of B, event B. So it basically means when B already happens, it must be an element that in the sample space, right? And then in the sample space, what is the probability that A happens? So intuitively, that means you need to get their intersect. It means this whole intersect space over this space gave you this quantity, which is the probability when B already happens, what is the chance that A also happens? So it's the intersect right here over the whole space of B happens. Right? So a conditional probability equals a probability of an intersection over the probability of the condition. So that is the rule of conditional probability. And then if you know this, remember my first question is, if you don't know anything about A or B independent or not, and you just want to estimate probability of A intersect B, how do you do that? And you do that by this rule of conditional probability. It means probability of A intersect B equals, you move this part right here. It means that the intersect of A and B equals the product of A happens conditional on B and then multiply then if you move this part to here, probability of A intersect B is the probability of A times probability of B conditional on A happens. Probably sounds a little bit confusing in the beginning, but if you understand the underlying derivation, it actually helps you to remember those formulas. So, what if they are independent? What I just said actually is a general case. You don't really know whether they're dependent or not. So, if they are independent, probability of A conditional on B is, like we said, the probability of intersection over probability of B, the conditional event. And then the probability of the intersect, if they are independent, that is a product of the two probability. So we get here, and then this term and this term canceled. So that means probability of A conditional on B, if A and B are independent, equals probability of A. And similarly, probability of B conditional on A, if they're independent, equals probability of B. So what does that mean? That means that if the two events are independent, then the first event probability of that happen conditional on the second event happen really doesn't change. It's just the marginal probability of the first event happens. And that goes very nicely with the independent assumption, because when you know that B happens, it gives you no advantage or disadvantage in knowing whether A happens or not. So when you know that B happens, the probability of A happens is just equals to the probability of A happens, because A and B are really independent. Intuitively, if you go back to the raining example, it basically tells you what is the probability of my chair breaks conditional on today is raining. That doesn't really help you a lot, because that probability is just equals to the probability that a chair breaks. Because that would be the same if that day is not raining, it's sunny, right? So probability of two independent events, the conditional probability equals the marginal probability. So intuitively, A and B, if they're independent, the event B really has no influence on the event A, and also the event B is not influenced by the event B. So raining and chair broke really has no impact and also not impacted by. Another thing, if A and B are mutually exclusive, then what is their conditional probability? If they are mutually exclusive, by definition, that means the probability of A intersect B is 0. So that means if A and B are mutually exclusive, probability of B conditional B happens conditional on A happens really is 0. Because if you think about it, this whole conditional probability is a ratio, and the numerator is a probability of their intersection. And by definition, if A and B are mutually exclusive, that means their intersection has probability 0. So mathematically, it makes sense. They're just 0. Intuitively, it also makes sense is if A and B are mutually exclusive, then conditional on A happens, we know that B has no likelihood or no possibility to happen. So it must be equal to 0. So going back to that raining example, if A event is raining today, and then B event is it's not raining, then the probability of not raining given it's raining is 0. And so after we know this conditional probability, it gives us a total probability rule. Total probability rule is phrased like this. For any event, so here remember, this applies to any event. It doesn't matter whether A or B is independent or not independent, exclusive or not inclusive. If you have any two events, probability of B equals the probability of B conditional on A multiplied by probability of A plus probability of B conditional on A complement multiplied by probability of A complement. So if you just see that mathematically, it's probably a little bit dry. But if you think about it, why this happens is because for any two event, you can decompose that in this way. So it essentially tells you this way. If this is the whole sample space, and then you have this event that's called B, and you want to learn the probability of B, there is this way that you can decompose that. Is you can randomly give another event A. This A doesn't have to be in any relationship with B. Okay? You can give this concept, and then the next step, you basically see, well, now B can be decomposed in two subsets. One subset is the part of the elements that intersect or overlap with A. So we have this example, which is a breast cancer example. So we have physicians recommend all women over age of 50 to be screened for breast cancer. And then this procedure is, the best thing that you can do is you can do a biopsy. However, this procedure is kind of expensive and also painful for a lot of women. So what do is you do a mammogram. And then, so you have two events here. One event is breast cancer, yes or no. And the other event is mammogram, yes, positive or negative. Ideally, the probability of breast cancer, yes or no, for the mammogram positive should be 1. And the probability of breast cancer among the women who are mammogram negative should be 0. So these two events ideally should be completely dependent. But the complete opposite extreme would be these two events are completely independent. Basically, that means the probability of breast cancer is the same regardless of mammogram positive or negative. So, to understand or to assess what their relationship, whether it's one extreme or the other extreme, or somewhere in between, we define this quantity called relative risk. So relative risk is actually some number or some definitions that you hear very frequently in epidemiology literature or in statistics. It basically tells you the relative risk of B given A is defined as the probability of B conditional on A over the probability of B conditional on A complement. So it's a ratio of two conditional probability. One is B conditional on A happens, and then the other one is the probability of B happens conditional on A doesn't happen. So by this way, if you think about it, if A and B are independent, which means known A doesn't have any information of known B, then the numerator is probability of B, and the denominator is the probability of B as well. Right? So that means if A and B are independent, the relative risk should be 1. And then if the relative risk is different from 1, that essentially means A and B are dependent. So relative risk is an epidemiological term to define dependence or not. Sometimes it's very convenient to use because this ratio really quantifies what is the relative risk of exposure A on the event B. So going back to our previous example, if we know that among 100,000 women and they have negative mammogram, and 20 of those will be diagnosed with breast cancer. And then, on the other hand, 1 woman in 10 with positive mammogram will be diagnosed with breast cancer. So, what does that mean? That means that probability conditional on A complement. So here, A represents a mammogram positive. So if A complement represent a mammogram negative. So probability of B, which is breast cancer, conditional on negative mammogram, that is estimated by 20 over 100,000. So this number right here, 0.0002. On the other hand, if A happens, so if mammogram is positive, probability of breast cancer, which is probability of B, conditional on this A term, is 1 in 10. So that's 0.1. So given these two conditional probability estimates, what you get is this relative risk of positive mammogram on breast cancer is defined as the ratio of those two conditional probability. So that's 500. So that this number quantifies that there's a very high dependence between mammogram results and breast cancer. So if you go back to that example that I was drawing on the Venn diagram, relative risk really defines the ratio of B conditional on A over B conditional on A complement. It gives you a relative kind of quantity that what is the relative ratio or what is the relative scale that B happens when A happen or not happen. So it have a very natural statistical explanation behind this relative risk. And then we can also use this total probability rule here. So suppose our purpose is trying to estimate probability of B. So trying to estimate the total prevalence of breast cancer in the general population. And suppose all you know is that 7% of general population will have positive mammogram in the next in your current sample. So here B is defined as a probability of breast cancer and A as defined as the probability of positive mammogram. And we know that probability of A is 7%. So that goes to my previous thing that if you know nothing about B, what you do is you decompose probability of B by the two parts. The part that overlap with A and the part that doesn't overlap with A. So that is a total probability rule. So using this rule, probability of B equals the probability of B happens conditional on A multiplied by the probability of A happens plus probability of B conditional on A complement multiplied by probability of A complement happens. And why do we do that? That is because we know the probability of A, which is 7% of positive mammogram. And we know that given the mammogram is positive, the probability of breast cancer is 1 in 10, so it's 0.1. And we also know that probability of A complement is just 1 minus the 7%, right? And we also know that if a woman is diagnosed has a mammogram negative, probability of breast cancer is 20 over 10 to the 5. So by this decomposition that you're trying to understand this unknown probability, you can decompose that into 4 numbers that to all of those you actually know, which is 0.1 multiplied by the prevalence of positive mammogram plus this 20 over 10 to the 5 multiplied by 1 subtract this 7%. So you got 0.007. The last concept that we are going to talk about today is called exhaustive events. A set of events is jointly or collectively exhaustive if at least one of the events must occur. So that means their union must cover all the events within the entire sample space. So, if A and B are collectively exhaustive, that means A union B is equal to the total sample space. It basically tells you that exhaustive events, they take all the space that's possible. They take all the space of your total sample space that is possible. So naturally, by definition, A and A complement will be defined as collectively exhaustive because A union A complement equals to the total sample space. If we extend it to more than 2 events, if we have a sequence or a set of events, A1 to AK, they are exhaustive if at least one of the events must occur, and also if they are mutually exclusive and exhaustive, that means at least one of the events must occur, and no 2 events can occur simultaneously. So what does that mean? That means if you run a random sample of this whole sample space, it has to be, your outcome has to be one of this A1 to AK. So at least one of this have to occur, and also joined together, they take over the whole sample space. And when one happens, it cannot be the other ones. And then if you think about this total probability, and you can actually generalize that into this mutually exclusive and exhaustive events. So probability B can be decomposed into this K component. And in each component, it's B conditional on AK multiplied by the probability of AK. And A1 to AK is exclusive and exhaustive events. So this probably seems a little bit complicated, but it's actually a natural extension of what we read there. So there we decompose the probability of B by 2 components. One is conditional on A, and the other one is conditional on A complement. So here, A and A complement basically means they are mutually exclusive and exhaustive. What if you want to decompose the probability of B by more than 2 components? And that is the general version. That means if you can find a series of events, the probability of B is basically the summation of those series of conditional events multiplied by the probability of each condition happens. Okay, so in the Venn diagram, look at this. In the Venn diagram, this can be understood as extension is if you want to estimate the probability of B, previously you put one set here and put its complement here. Now you just put a lot of sets here. You define a series or a set of sets or a set of events, and all those events are mutually exclusive, and altogether they take upon the whole space. So those series of events is mutually exclusive and exhaustive. And then the probability of B is just the summation of each small set. And because this whole sets, they are exhaustive, so they take the whole space of B. Remember, it's just decomposed by a lot of small parts. So probability of B really is just a summation of B conditional on AI times probability of AI. Okay, so we have finished today all the concepts that we want to introduce. So today, remember, we talked about probability. And probability is a quantity that quantifies randomness or quantifies the likelihood of any event happens. So it's study of randomness. And then there are several basic rules of probability. One, it's always bounded, 0 and 1. And second one is we talk about mutually exclusive events. We also talk about mutually independent events. And then we introduce addition law of probability, which is used to estimate the union. We talked about the multiplication law of probability, which is used to estimate the intercept. And then we talked about conditional probability, and conditional probability is really used to estimate the intercept of two events, whether or not they are independent or not. And then from the concept of conditional probability, we emphasize that if A and B are independent, their conditional probability is equal to their marginal probability. And the last one is the total probability rule is equals to the summation of all the composition. And the composition is composed by different sets of mutually exclusive and exhaustive events. That's it. And this one gives you a flavor of the next lecture. Thank you. Oh, yeah. Do this? No, that's it.